Good morning, everyone, and welcome to Why Are HVAC Systems Not Equal? I want to thank everybody for coming this morning. And first of all, I'd like to thank the MBA for inviting me. Second of all, I'd like to thank the person on my left, your right, Craig McGarry. He helped put this together, did most of the work, as a matter of fact. And thirdly, we're just going to go over a few things in HVAC that maybe or maybe you don't know. And I put HVAC up here, heating, ventilating, and cooling. That's what the acronym HVAC stands for. First, some introductions. I'm Neil Solheim, the construction manager at Quality Heating and Sheet Metal, a 40-year veteran on the war of discomfort. People have been complaining about discomfort for years and years and years. We've been trying to correct that by putting furnaces, air conditioning, and maybe some cleaning in the homes. But I'm going to start out, I don't have a joke. I have an apology. The reason I have an apology is when I started out my apprenticeship, one of my jobs was to put a screen. Can you get the duct up there? There we go. To put a screen in the bottom of this end cap. That was my job. For months and months, I did that in the winter. I'd put that screen in there. And this screen actually would be installed in the bottom of this return drop right here. It was a return air in the basement. It actually worked out quite well. The problem is, I found out years later that it didn't meet code. It's actually illegal. You can't do it. So for all of you that have screens in the bottom of your return drops, I apologize. We've been taking them out for the past 25 years. So far, nobody's gotten hurt in it or anything with it, but it was a code violation that we were doing. I do practice safer HVAC now.
Why was it a code violation?
Well, the code says that we cannot have a return in the same room as the equipment. So the code is still in effect today, so if we have a furnace, we can only have a return in a separate room. It cannot be in the room where the unit is. And that included a wide open basement. Good question. Well, beside a coffee buzz this morning, at the conclusion of this class, you're going to have a basic understanding of the history and workings of a modern forced air HVAC system. You'll be able to identify a good system from maybe a not quite so good. Maybe it could use a little improvement. You'll get the knowledge to ask appropriate questions to your HVAC contractor to select the desired level of comfort that your customer really deserves. Today I'm going to focus mostly on forced air. I will entertain questions after the class on other systems like hydronic, geo, things of that nature. We're going to focus mostly on forced air today. Historically, comfort started with fire. When the caveman had fire, he had comfort. That's not quite what we're trying to do today. We'd like to have a little better comfort. So we went a step further. And I don't really remember this lady. She was the lady that took her kid to the tanning booth. Well, fire gives you radiant heat. And this lady obviously likes the radiant heat that she gets from the sunlight to the point that kind of tanned her up pretty good there. The problem with radiant heat is if you remember when you're standing around a campfire, the front side of you would be nice and warm and toasty. But what about the backside? Your backside would always be cold, just like when you wore that old hospital gown. That was kind of comfort, but not what we expect today. Go on. Then we started with these things. We had this monster in the basement. This is an old coal furnace. In the late 1800s, about the same time the Hatfield McCoys were going at it, these coal-fired furnaces were brought in. They had big plenums. They looked kind of like monsters. But that was the new thing. That was comfort. But it's not comfort like we'd like to see anymore. We kind of evolved into something else. And then we went into the big old oil-fired furnace with lots of big ducts on it. Still a monster in the basement. This was the next big thing in comfort. After that, bingo. This is the modern furnace that we've been using since about the 1940s up until maybe a year ago. This furnace had a chimney vent on it, and it had a blower on it, created comfort, and this was the standard for many, many years. Now, you have to understand, the efficiency of these things started out about 50%. When we got done in the late 80s, we'd hit about 80% with these. Comfortable, but we're still not quite there yet. We haven't gotten to our comfort point. The next thing that happened with these older furnaces, they were one-speed. One-speed furnaces. What happened is it'd be like getting in your car, putting your foot down, hang on, you're driving at your fastest speed that your car can go, then you'd shut it off. Coast a little bit, turn it on, let's go again. That's what we were doing. You ever see some of the people in Florida, how they drive? You know, driving those big old cars and stuff. Foot down, stop, foot down, stop. Well, that's how our furnaces operated. In fact, right now we still have furnaces that operate this way. What we're looking at now for furnaces, we want it to be constant. We want our heat to be smooth, constant. We don't want up and down temperatures. We want it to be nice and smooth and constant. So we take these big up and downs, we try to smooth them out a little bit, in kind of a nice closer sine wave than we had where we had up and down, on, off, on, off. We want them to be a little bit smoother than they were. So we now have furnaces. I got to put a disclaimer on this. It has a brand name on it. This is not brand specific today. It's just we happen to pull a picture out with a name on it. But the furnaces now, we're looking for comfort, quiet, and efficient. How do we achieve this? What we're looking at now is we now have furnaces that are 98% efficient. I mean, that's as close as we can get. 98% efficient in the burning process. That's pretty darn good. The next big thing is down in the bottom we have these motors. It's called the ECM motor. The thing I like about these motors is that they run on low speed with the equivalency of about a 60-watt light bulb. So when you have that fan running 24/7, continuous, you know, it's easy for us to say to the homeowner, you know what? I know you don't want to leave all your lights on, but your blower is running at the equivalent of one little light bulb. You're going to get comfort by having that fan run continuous at the cost of a light bulb. Another thing I like about that blower, that ECM blower motor, it's made in Beloit, Wisconsin. Regal Beloit bought the patents and everything from GE, who developed the motor, and it's made here in Wisconsin. That's a good thing, a nice hometown brand that we are working with. So the other part of it is, up in the burner section here, we now have gas valves that modulate. And what that means is, well, maybe not this morning, but a few mornings ago it was kind of cool out. Those gas burners would come on, and on that 80,000 BTU furnace, we might be running at 20,000 BTUs. That's all we needed to heat the house. When it's 10 below zero, we need all 80,000 BTUs. But we don't need it all coming out at one shot like we saw on the previous slide. So the gas valves will modulate and put a nice, steady, even heat into the building. Now we're talking comfort. This is how we're starting to win the war on discomfort. The next thing that comes in the war on discomfort is we have to start doing some calculations. Years ago, we would size a furnace based on no science. We'd say, well, you got a house, you need a big furnace. In fact, when I first started out in the city of Brookfield, they dictated, the building department dictated to us what size furnace we'd put in the house. Turns out later that they discovered and we discovered it was about double the size. Well, goodness gracious. What did we do for the consumer? We put in oversized equipment that started and stopped all the time, herky-jerky, and cost a lot of money to operate. Ooh, boy, wasn't that a good idea? Well, now we do calculations. We do the res check calculation, which is the whole load of the building, but it really doesn't tell us what's going on in the house, especially in each room. Consequently, we do these loads. Computer loads, and we can do it, and we can figure out the amount of heat and cooling required to each one of the rooms and the amount of air that's required to go to each one of the rooms. Sounds easy, but it's some work that we have to do. The next part of it is we have to do good design. Now, we're going to see a few slides here. Just hold it. If we look at this one right here, this is what we call in the trade a square throat elbow. See how the elbow is a 90-degree angle? I'll talk about a little more of that in just a minute. That square throat elbow is bad news. The reason I say it's bad news is when we do duct design, we base everything on what we call equivalent feet. This elbow is the equivalent of 75 feet of straight duct. 75 feet. I'll show you how to correct that later on. This, does it need an explanation? I think that's either that's an alien furnace system or silver spaghetti. I don't know. Believe it or not, this probably could work if it was sized correctly, but I don't know, it doesn't look the best. Here's more things. You know, in our system, in a good system, we need to seal our ductwork. Well, this doesn't look very sealed. Doesn't even look like it's even connected. But we have to be cognizant of what we're doing in our system to make sure we have sealed, assembled duct systems. And then we have the use of flex. Now, I'm going to quantify this. There's nothing wrong with flex. The only thing wrong with flex is the operator. If you guys have dogs, you understand that dogs will learn from their owner, and if the dog doesn't learn, it's really the owner, not the dog. Well, that's what it is here too. The installer and designer of flex can make or break flex. And flex gets a bad name only because of the operators. If it's installed correctly and sized correctly, it works. Here we go back to design again. The best unit in the world that's 98% efficient will only operate at 60% efficient if we don't have a good duct system in the house. And the next thing is, God bless her, that's Betty White, obviously. She's our elderly person representing us. The big key is we don't want to blow air on people. We want to blow air along the wall, along the ceiling, but never on people. So how do we achieve that? The lowly little floor register. I did a seminar, probably 6 years ago now, about using floor registers over baseboard. Well, just a quick review on that. Up until the year 2000, southeastern Wisconsin was the largest, buyer of baseboard registers. The only problem with a baseboard register, it doesn't throw the air along the wall, it throws the air out in the room. When it throws it out on the room, it throws it on Betty White. She doesn't like a draft. So we like to use floor registers so we can control that air, throw it up against the wall. We don't throw it on people. They don't feel drafty then. That's a big thing. Another thing that's happening too, and you're going to hear more about this, is with these buildings now, there's a new rating called HERS, HERS, a HERS rating. This is kind of coming in, and it's sort of in its infancy, and you're going to hear more about this because this is for builders and architects. What it does, it kind of gives the building a miles per gallon chart. So what's going to happen, you're going to include your furnace and air conditioning and the performance of the building and everything, and it's going to get a number. I don't know exactly how that's all shaking out yet, but it's coming to town. So we're going to hear more about that HERS thing. Where we come in with HVAC, we're going to be designing systems again to help builders achieve this HERS rating. Because what's going to happen in the future is when you go to sell your home, the realtor is going to ask, well, what is the HERS rating? Well, that's the same question they're asking, what is the miles per gallon of your car? 20 years ago, we didn't care. 30 years ago, we didn't care. We're starting to care what the miles per gallon on our car is. People are also going to get more cognizant of what is the efficiency ratio of a home. So that'll be coming in the future. That's a little tickler for the future. We're going to go back to that elbow that we saw. And this is sort of our secret about duct design as an industry. We really don't do a real good job of it. We just kind of put some ductwork in and hope that it works. But basically what happens when we install duct systems, all the charts and manuals are based on 100 equivalent feet. Well, we saw that elbow previously, that's 75. That uses a lot of the equivalent footage to go from the air handler all the way out to our diffuser. So we have to use good duct design. What's that going to do? Here's our lowly little 6-inch elbow. I'm going to do a little demonstration with that right now. This elbow is the equivalent of 10 feet of pipe. We kind of know this because we size for dryer vents and things like that. Doesn't matter what size the elbow is, this is 10 feet of pipe. Simple math is 10 plus 10 equals 20. Here's the problem. When we put two elbows together like this is what a plumber calls a swing 90. We call it 30 equivalent feet of pipe. You get penalized by putting two elbows together that are closer than 2 feet apart, because the air doesn't have time to fix itself before it gets to the next fitting. So when we put elbow on elbow on elbow, we have a lot of turbulence going on, bad equivalent footage. So 10 plus 10 does not equal 20 in this case, it equals 30. These are some of the things we have to work on. The next thing, we saw the slide, and here it is again, of the square throat elbow. 75 equivalent feet. That's a lot of equivalent footage. What we found out in the 80s is that we always thought the radius, the back part of the heel, was the important part. What we found out really is that the throat is the important part. When we have a radius throat like this, that changes that elbow from 75 feet to about 20. That is a big, 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 big difference. So consequently, when we make choices as an HVAC contractor, we do this. Now I know what's going to happen on Wednesday. I'm going to get calls from other HVAC contractors, and they say, Neil, what are you doing again? Giving away our secrets, giving away our dirty little secrets. Now everybody has to use radius throats. Well, yeah, that's what I'm trying to get across. We need to buy a better fitting to get a better performance, to win the war on comfort. That's what we're doing. Is there any more up there? There's our radius elbow. And there's a boot. That's fine. And then we just have to buy better fittings to make this system work better by using low restrictive air fittings. And that's what the radius throat elbow is. This one? That has square angles on it. This one, believe it or not, is 30 equivalent feet. Here's the thing about it. It's at the absolute end of the run. So it only affects itself. This one probably affects 3, 5, or 10 other branch runs. So we always try to do a better job closest to the furnace. Sometimes we just don't have a way of counteracting this. So when we do all the calculations and add everything up, yeah, we have to take that into account that this is going to be 30. That is one way to compensate it. If it's a bigger, if we increase the size of the duct, that will actually reduce the equivalent footage. There's other fittings that can be used for that too. We can use a straight boot and an elbow, and that cuts it in half. The only problem is it doesn't work so good in the basement. You know, then it's hanging below the joist, and there goes the rec room again. Good question. Okay. The other thing that happens with that too is when we use better fittings, what happens with that is we actually use less electrical power on the blower. It's kind of a hidden secret, but what happens is if we have a better duct system, it takes less horsepower to push the air to where we want it to go. You know, years ago, in commercial, the design engineer would say, well, we'll just add more horsepower to the blower. Those days are kind of over now. We can't do that. We have to do better duct design because more horsepower equals more electric usage. Higher utility bills, that's all going to have an effect with this HERS rating that will come to town in the future. So we want to get some benefits from a good duct system for the owner by having lower utility bills. And it's not just a gas bill, it's also their electric bill. Okay. There again is calculations, 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 calculations. Duct standards, calculations will give us all the good installation practice of the fittings. Well, it's time to do some install. Let's see what we have next. Okay, here's our bath fan. I'm sure you've seen seminars or information from Joe Nagin talks about a good bath vent. Well, this is not a good bath vent, but we still see this. A couple things that are going on here right now. One of the obvious is, would you say the flex could be a problem? Not stretched out, correct. Another problem is too, when we put two elbows together, we have a problem. Just like if we have flex too close together bending, it's a problem. But if you ever look at a Brown installation manual, it'll tell you to run out 2 feet straight before you turn a corner. Okay? It's just a little practice that we're trying to accomplish now, that we want to have the duct run out 2 feet before it turns a corner off that fan. That's what Brown recommends. That's what good design recommends. Collectively, as builders, contractors, and homeowners, that's what we would like to see too. So we really would like to let the HVAC guy kind of design the size of the fan, because we sort of know what is required in that room by doing a calculation. Plus, if we install a fan, then we can eliminate things like this, because no offense to electricians in the crowd, I saw one, they don't really know that when they put the flex onto it and turn it right away, that they cause the issue. We wouldn't expect them to know that. But when we do an installation, we make sure that we run it out 2 feet before we turn a corner. So that's a good installation. During rough-in, right now there's a code that kind of is telling us that we need to make a register layout for the building inspector. The only problem with that register layout, it doesn't take into account ductwork, sizing, or anything of that nature. I really believe that that was put in place because people were putting their furniture over the registers and it was causing an issue. It really doesn't do any design. So the key to all this is design. Design, execution, and testing. Right here we have some installation. It looks like it's pretty good. Here's some more installation. Looks like it's pretty good, except I see a square throat elbow. Here's some more installation. Looks okay to me. Probably could use some duct sealant on it. And here's some more installation. And this is all in the rough. The interesting thing about the rough, I have a cat. My cat goes down in a litter box, does its doo-doo, and covers it. I feel sometimes that's what we as an industry is doing. We'll put all our stuff in the rough, cover it up. We don't know what we did wrong. You have to check, double check, triple check, make sure that everything is in place. We don't want to have leaks. We don't want to have leaks around the returns. We want to make sure all the ducts are connected. We have to make sure that everything is complete in the rough. That's very, very important. I'll get a call on that Wednesday, too, from other contractors. Double check, triple check. Go ahead. Once we get into the duct system, it's time to start doing the installation in the basement. Now, there again, not brand specific, but we're looking at a media filter here. What we have here is a media filter. Now, this particular filter has a MERV, M-E-R-V rating of 11. The higher the number, the better the filter. This filter doesn't list a MERV rating on here, but we're guessing it's 1 to 2, something like that. Well, more importantly, this filter fits into a rack like this with a pretty big opening. It doesn't fit tight. Well, guess what? We found out there's as much air leakage around this thing than it was of this guy that I used to do a long time ago. We have to eliminate the air leakage like this. We also have to eliminate it this. So here we have air leakage and a lousy filter where we could have a good quality MERV filter in a cabinet that has a gasket on it. This sealed cabinet prevents all that leakage, and then we have a good filter. Well, why would we do anything else? I don't know why, but we still do. So consequently, part of the war on discomfort is to get a good filter in for the consumer. Not just to protect the furnace. Let's clean a little bit of air. So the air is a little bit cleaner for the people, the occupants of the building. That's really what we're trying to do. Part of the war on discomfort. Let's get it fixed up. I mentioned a MERV 11. The highest filter rating I know of is a 17. That's called a HEPA filter. We historically haven't used a lot of those because you need a separate blower to work for them. They're really, really good if someone has some severe allergies. But this MERV 11 filter has been, some are 10, some are 11, are doing a great job. Gets a lot of air through it, cleans everything up real good. Okay, the next little part of this is commissioning. It's kind of interesting. We put a furnace in, just like the battleship, we need to commission it. We need to make sure that it's going to do what we think it's going to do. Because air is kind of a weird duck. It's going to go wherever it wants. It doesn't go where you really want it to. You have to kind of force it sometimes. So it's really a good idea to do commissioning and startup on a system. So when a technician puts his gauges on it, he's trying to do a few things. First of all, he's going to make sure that the blower is operating the way it should be. Because guess what? The new furnace has 5 blower settings. 5. And that's not even the one with the variable speed or anything. But the standard furnace now has 5 blower settings. The guy at the factory, or the person at the factory putting it together, has no idea what kind of airflow that you're going to need in the house you're putting that furnace in. So unless you look at it, and whatever settings it comes from the factory, you don't know. You don't know until you test it. So you have to test the system to see if you're getting the proper amount of air across it that you claim it's going to be with all the design that you've done. Please test. Another thing, a furnace is designed to operate in what we call a temperature rise. In the temperature rise, we have air that goes across the furnace, and they give us a chart that every furnace is a little bit different, but it's generally rise of 30 to maybe 70 degrees at the most. So what that means is, let's say we have 60-degree air coming into the furnace. And we have a 70-degree temperature rise, that's 130 degrees. Well, that's what the temperature output is on that furnace, 70 degrees. But if we test it, and it tests out at 140 degrees, when all of a sudden we have a little bit of a problem. It means we don't have enough air going through that furnace. But we have 5 blower speeds. We can make it work. Conversely, we've already tested systems where we have a 20-degree temperature rise. Well, the reason this happens, and this is more common now than ever, because all the furnace manufacturers are trying to get the most efficiency rating out of their unit they can. So they're coming along and they're testing these furnaces with all the laboratories on high speed. Well, that's okay, except when we're trying to blow air into a house, we don't need all that speed, and we don't want to be blowing cold air on elderly or people. So there again, if you don't test it, you'll never know. You could have a 28-degree temperature rise, boom. We're talking, we lost the war on comfort. Because unless we get it between the factory specifications, they're not comfortable. So that's what this is all about. We're doing all this to win the war on discomfort. What else do we have to do? Another thing too. These furnace blowers are so darn powerful now. They're incredible. I've already seen it where the air conditioning coil is wet and it's trying to get water and it runs down in the pan. I've already seen it where the blower has actually blown the water off of the coil. It is blowing that air that fast. Well, guess what? We could be creating high humidity in a furnace. I don't want to use the M word. But more importantly, we're not dehumidifying. So all of a sudden, we get into a situation where a customer will call us and say, hey, guess what? My house is cool, but it doesn't feel good. I feel like I'm cool and clammy, like I'm in a cave. We know right away what happened is we didn't adjust the blower speed. You have to get that blower speed matched to the coil, matched to the amount of air, and there it is, testing, testing, testing again. So we must test. This will help us with our battle on discomfort. We get that heating speed proper for heating, cooling speed proper to dehumidify. We're going to be in good shape. The homeowner. You know, it's kind of interesting. You know, if you ever buy a new car, that salesperson will not let you leave with that car unless they go over the features of it. Try to do it. They won't let you go. They don't want to have that call the next day, well, what was this? What was that? You know, I hit the pole because I didn't know where the brake was. You know, you're not going to get it. And yet, we as an industry tell the new homeowner, hey, go ahead, move in your house, it's okay. Well, what do I do? What do I do? Where's my thermostat? Where's my light switches? When a technician walks through the house with a new homeowner, they're overwhelmed. But at least they'll know some of the things to do. They might take a few notes. You might give them a little written instruction on what to do. But it's very, very important. We've had customers call up, and they've called up and they said, you know, I've been in my house 3 years now. Where's the filter? Whoa, 3 years. Where's the filter? You haven't had a service call yet? That your furnace doesn't work? Whoa. You know, when we get a call like that, all I can say is I'm embarrassed because we didn't do our job properly. I mean, the person really should at least know where the filter is or sign up for some kind of maintenance contract or something. But it happens. And that's why we as builders really have to start doing a better job, and contractors, to get the information out to the owners. They really, really need to get a basic of what their system is. You know, we don't expect them to look at the furnace and check the blinking lights in it and things like that. But what we've also found is the new consumer is pretty astute, pretty good with their iPad and everything. They will look at the blinking lights in the furnace and tell you what the problem is. It's like, ooh, okay, very good, guys. But that's what happens. The consumer is getting more aware and less tolerant. When the consumer buys that new car and they get their basic instructions, they get in and drive it, it's trouble-free. They're expecting that with us. They're expecting the comfort and the satisfaction of it. We have to give it to them. So, what's the full circle synopsis here of how are we going to close this together? Design. We must do design. I see some engineer types in the audience here. That's all they do is design. You know, they're kind of laughing, going, well, how can you do a heating system if you didn't do any design? What about room-by-room heat losses? Most of the homes out there do not really have a room-room heat loss. Every commercial job that's done is required, but it's not required in a home. Heat gain calculations. When we do the res check, or when the architect or the designer does a res check for a house, that doesn't tell us how much cooling to put in a house. We have to do a calculation for that. And guess what? I found out that the builders were a little sneaky, and they did something they didn't tell us. All of a sudden, they started putting in very, very good windows. Low E, good sunshade, solar coefficients. Guess what? We were oversizing air conditioning units because we weren't taking that into account. Now, by using these calculations, it's kind of eye-opening to find out what size equipment is really going in these houses. Because I hear in some circles, they call it zero energy, extreme low energy. Well, guess what? Just a standard builder model home that's being built now is very darn efficient. It's very efficient. We have to account for that. We have to correctly size that furnace and the air conditioning unit. Too big of a unit will not dehumidify. The people will feel cold and clammy. We had that happen about 3 years ago. We had a model that was being built forever. And all of a sudden, the new windows came in, the new insulation practices and everything, and all of a sudden the people called up and they said, hey, we are not comfortable. Okay. We did too big of an air conditioning unit for you. Sorry. Bigger is not always better, especially in our industry. So we do the calculations with this manual J. Select equipment. Now we really still can sell you equipment as an industry that Foot all the way down, back up. Foot all the way down, back up. Why? Why? Let's start using the good equipment. Multi-stage, ECM motors that come out of Beloit. And let's proper size it. Let's get those blower speeds set properly. Same thing with the efficiency. There's not a whole lot. You know, you'll hear salespeople talk, yeah, but our unit's 95.5% efficient. Ours is 97.5. You know, when you're up in that range, that couple of percent is not going to make a big difference. Now we're talking comfort. That little bit of percent is the result of building a good furnace that will give you great comfort. Matching the system to a consumer. Many years ago, we had the opportunity to do an installation for a doctor. Hey, God bless the doctors, they do a great job. What I didn't know is this guy was a surgeon. Being a surgeon, it turns out, he told me that he lives in an environment that is 67 degrees. So at 67 degrees, he said, you know, Neil, he says, I apologize, I should have told you that. I don't want it 74 degrees in my house. I want it 70 degrees. I'm like, okay, that's sort of out of the realm of what we're doing, but we need to match our systems to the consumer. Some consumers have allergies. They have all kinds of issues that they need to be worked on. They need more components. They might need an ultraviolet light to kill bacteria that's floating in the air. There are things that are out there that we can do. But we really need to match our systems to what the consumer needs. We're not just trying to sell stuff. Well, we are, but you know, we still like to match it to the consumer. And then the comfort level. Some people have a tolerance of comfort which is this big. You know, if it's between 60 degrees and 88, they're good. Some people, 72, that's it. That's it. 72. When we do a survey, when we're doing like a replacement sale or even a new construction sale, and we speak with the owner, we ask what their comfort level expectation is. And some people will tell you. They say, oh, I had a house I lived in, it was terrible, I could never heat it, never cool it, blah, blah, blah. I like to be at this temperature, blah, blah, blah. People will really tell you what they need. So we need to find out what their comfort level is, and there again, that's matching our system to the customer. So the bottom line is, we have to select systems that will help us all win this war on discomfort. It sounds profound, it sounds silly, but we really need to do that. Can you go back again? Can you go back? Go back. We really need to do that because it's not just a furnace anymore. It's filtering, air conditioning systems, humidifiers, energy recovery ventilators, ultraviolet lights, thermostats that basically almost think for us now. These are the things that we have to really look at for the consumer. So, there again, it comes back to planning. We have to plan. We have to have a good plan. We have to work with the architect and designer. Because when we're working with that architect and designer, I'm not picking on architect and designers today, but we have to have a place to put ductwork. If we don't have a place to put ductwork in that building, it's kind of hard to get the assured airflow that we're looking for to that northwest corner bedroom where the baby is going to move into. Okay? We need to have a duct path. There again, from start to finish, from the plan to building to commissioning the house, these are all the things that we're looking at. Of course, the installation has to be done professionally and has to be done to standards with good design on it. Make sure the communication is out there. Use low friction fittings like we looked at. and seal the ductwork. 20 years ago, we didn't care about sealing ductwork. We just let it leak into the basement and let it go. Now, we want to make sure that we get every little CFM of air to the corner bedroom that we say we're going to do. So that's why we seal the ductwork. When we're done with the system, it's complete, looks good, performs well. That's what's going to win the war on discomfort. Commission it, start it, correct the airflow settings, balance to the calculations. This is a little controversial because some building inspectors request a balance report for the home. Well, the Uniform Dwelling Code really does not put it that way. We have some inspectors that request these calculations. The catch-22 about that is you cannot give a balance report unless you've done a calculation to get to a balance report. Most of the inspectors recognize that, but we're still kind of having a fight with a few of them. They're requesting these calculations, but they can't really legally do that under Uniform Dwelling Code. Clean the filters. That really stinks when the homeowner moves in and 2 months later and says, hey, my filter's clogged up. We don't like that. Let's get a clean filter in for them. We always like to have 2 of these filters on a job site, one during construction, one later on. Owner instruction, care and use of the system, and, of course, here we're instructing the homeowner. I don't know if you recognize this guy, but we're instructing the homeowner, and he's kind of telling us that he says, hey, we have an operating system book on how to operate your home. You show me how to use the furnace, I'll show you that I wrote a book on how to operate the home. This is kind of a good step. This is kind of a neat thing. If we did this as builders and HVAC contractors, we'd all be a lot happier. Questions, comments, criticisms? Forced air systems, anything else, anything you have in your mind? Yes, sir.
What's the name of the book and who's the author?
Well, I'll give you the name of the author.
Okay.
That's Tom Feza, Mr. Fix-It.
Oh.
He promotes his book in numerous areas. We worked with him on his home. He did a lot of testing on his home. He was working on comfort, working on cleaning, working on efficiency, did all kinds of tests. He kind of made his HVAC system his guinea pig experiment. Fortunately for us, it kind of worked out, I guess. Everything worked. We kind of passed his mustard, so it worked out okay. Yes?
Ventilation systems.
Yes.
With the heat exchangers and stuff?
Yes.
You guys do a lot of that stuff, or isn't that, because I don't know, the houses are so tight that, the complaints come in that they're
Great question.
too tight, and nobody wants to spend the money to do that, but that's something I think that's important.
That's a very excellent question. Okay, in the state of Wisconsin, we have what we call a required makeup air. This required makeup air was developed many years ago by a building inspector, believe it or not. And the way that worked is we had a particular builder that was putting in fireplaces in all their houses, and they were getting backdrafts and the furnaces would trip out. So we finally put this little pipe in the side of the house. We didn't invent it. It was just something that we started doing. The problem went away. The building inspector caught on and said, hey, maybe we need to do this. So the guys up at the state figured out a little formula based on half science, but got this figured out. So we put in a makeup air system in every new home now. We do a calculation based on the quantity and the CFM of the bath fans, dryer vent, hood vent, and we put it in. So what happened is we don't have as bad of a problem in other areas of the country because we have ventilation that's coming in. It's not really efficient because we're bringing in minus 10 degree air into our furnace system that has to get warmed up. The reference was to a heat exchanger or energy recovery ventilator. Well, that sort of softens the amount of temperature that we're bringing into the building. So that works out pretty good in that regard. Some of the ventilation guys like Joe Nagin are not a real big fan of the air exchangers only because he's looking at it at what we have now and the cost benefit of it. He's determined that he can't quantify the amount of savings that we put in from an air exchanger. We do know there is a savings, but there again, no one's been able to put the dollar amount to it. So that's why we don't see them as much as we should. But they are a definite benefit, especially if you're running ventilation 24/7, someone that has needs for a lot of ventilation air. Good question.
I thought that at one time I heard from one of those seminars that you can actually control humidity and stuff like that in your house by having that kind of system.
Well, the makeup air system actually is controlling the humidity too. In the middle of winter, when it's real dry air, we're bringing in that dry air, we're lowering the humidity in the house. We're actually doing that to the point that we like it because 2 to 3 years later, the homeowner calls up and says, hey, you know, I give up. We need a humidifier. Okay, we'll come and put a humidifier on. Builders do not want us to put it on because, you know, we all know when the home is brand new, we're talking about there's a lot of moisture in the house from the painting and all the processes that are going on in the building. So we don't push humidifiers at new construction. Some of the guys that put in lots of wood floors do want a humidifier because they know in a year or two they'll need it. But we do reduce the humidity with a makeup air, and the air exchanger will also reduce the humidity. But there again, we get to that balance point that we have to add humidity back in.
Well, what would you say, what in the wintertime, what's a good humidity? 30, I've heard it was supposed to be something between like 35 to 40%.
Oh boy.
Any more than that?
Oh boy, this is the controversy. I love this question. Very, very, very good question. Okay, now, here comes the female factor. You know, Mars, Venus, we got to do it. Okay, ladies like to have humidity at least 50%. It's good for the skin, keeps it supple, they don't need as many moisturizers. I'm not going there. I lived with my wife for 20-some years. I know what it's like. I'm not getting in that argument. Your building does not like 50% humidity. As soon as you get over 50%, we can start making mold. Less than 50%, we're okay, but depending on the temperature outside, the windows will get condensation on them with the amount of humidity inside and the amount of humidity out and the temperature outside. So to answer your question specifically, we like to say in the winter 35%. When it gets down to 0, no. Unless you have super, 4-pane glass windows or something like that that won't condensate, then that humidity has to start ramping down, 30, 25, 20%. If it's 20 below 0 for 2 weeks, you're probably talking about 15%. So that's what the problem is. The comfort level is different than what the building level is for humidity in the winter.
I'm just saying because we had some problems where the people were complaining about everything sweating in the windows and stuff. And you go in there and you set a humidistat on the kitchen counter, walk around, look around a little bit, come back at 10 minutes later and look, and it's like 75 or 70% humidity in the house.
Ouch.
It's 10 degrees outside. What do you think is going to happen to this place,
Right.
I just see that there was more problem with humidity than not having, than being dry,
Right.
I've had plenty of humidity problems, and nobody ever called me and told me their house was too dry.
Well, what typically happens, though, if people are using their home and they've been instructed properly, and that would be bath fans on a timer to purge out moisture from that 20-minute long hot shower. If you have pets in the house, you need to kind of move some humidity out of the building because pets can, cause humidity levels to go up. People really don't generate a lot of humidity. And the lifestyles that we live now don't generate a lot of humidity anymore. People cook in a microwave, unless you're boiling a lot of pasta or potatoes on the stove, you're not adding a lot of moisture just from your processes. Our dryers are vented outside. We're kind of we don't have as much humidity as we used to. But if we do have excess humidity, then it's use the fans, make sure that the makeup air is on, make sure that fan on the blower is running continuous to circulate air around the home, And then if it gets to an extreme, then we need to actually have a dehumidifier. And I'm not talking about a dehumidifier from the box stores. I'm talking about a good commercial dehumidifier that will actually work.
Can that be put right in a furnace and right into the system?
Yes. Yes. A commercial dehumidifier either by Aprilaire, Honeywell, or Thermistor out of Madison has duct ports on it that we can connect it directly into the furnace. And that will help dehumidify. And they work well. See, the key to this is you buy a humidifier from a box store, they might say 40 pint, but if you look at the key on that, it'll say 40 pint at 70 degrees. Well, guess what? Not too many people keep their humidifier upstairs. It's in the basement where it's 60 degrees. You look at the rating at 60 degrees, it might be 18 pints. So unless you have a commercial style, professional humidifier, you're not getting the humidity removal that you think you are. You know, they'll work. And the other part of that too is, if I'm not mistaken, maybe you can corroborate this, the box store humidifier will run at double the energy cost as a commercial.
She's running your you know, LG or whatever that you're picking up at the big box stores running. It's got to be put on a 15-amp circuit. The bigger dehumidifiers that, like Neil mentioned, the Honeywell, the Aprilaire, they're running anywhere down to 5 to 7 amp draw. So they're doing more, you know, dehumidification at a substantially less cost.
What would be the cost for something like that for, say, a 2,000 square foot home?
Well, typically a central dehumidifier, you can expect to pay anywhere from $1,800 to $2,500 for an installation.
And that would be the same for retrofit?
Well, retrofit sometimes can be even a little less because you can just use a commercial standalone in a basement. You don't necessarily have to have that ducted. Any other questions?
Going back to the makeup air.
Yes.
I have an older home. I'm on the second furnace on there, and it's mid-80s efficiency. Now with exhaust fans and the range, the hood, is there something? Because I notice when a furnace kicks in the wintertime, I mean you can feel the cold air just rolling through the exterior
Sure.
walls through the outlets.
Sure.
What can be done? I mean, is it?
Do you have a makeup air or no?
No, there is not.
Well, and that's one of the benefits of the makeup air also, because what it does, it takes that cold air from outside and puts it right into the return or thereabouts of the furnace system. Mixes with the house air, is warmed up through the unit, and that way it kind of cuts down on some of that air infiltration that you're describing. So you're introducing it in a controlled method as opposed to an uncontrolled method coming through the windows and doors and everything.
Is there a minimum height off the ground that should be pulled from?
Well, ideally,
I'd like to try something.
right. You know, ideally, you'd like it to be 2 feet above the ground, ideally. The reality is that most of the homes take the makeup air out of the skirt, the sidewall of the box sill. Consequently, there can be as little as 6 to 8 inches above the grade. You just have to monitor that because they will pick up leaves and debris and grass clippings and things of that nature. But in the back of the Uniform Dwelling Code book, there's actually a page that we're required to fill out for some of the building inspectors, and the formulas and CFMs of some appliances are listed in there. So you can add up all those appliances, use this formula, and actually come up with the size for your particular application. Good question. Anyone else? Yes?
On older homes where they don't have the vapor barrier on the ceilings, they just have the drywall,
Mm-hmm.
and today people are filling their attics with a lot of insulation. I've just been noticing through the last couple of years or whatever that there seems to be a bigger mold contribution. There has to be a reason why this is happening, and I was thinking that maybe the insulation they're putting in, does that hold moisture in there? People are running their humidifiers, and what is the biggest contributor of
Yeah, I don't
mold in the attics, other than the vent fans going to the soffits?
Okay. I don't profess to be a 100% expert on insulation, but I'll give it sort of a fringe of how it interacts with HVAC. In the particular case that you're referring to, is that first of all bath fans need to be vented to the outside. Venting to the soffit is okay, long as it's not within 4 feet of the proximity of another soffit louver that's drawing air up into the attic, because otherwise it'll just recirculate and go right into the attic. Okay, so that's the first thing that needs to be done. Second thing that needs to be done is use the fan. A lot of people don't use the fan. Third thing I know of is to make sure the cold side venting is proper, so any moisture that does get up into that insulation can be expelled through the venting system. And of course with the last part of it is we're talking about the, when you add more insulation, you better check the charts and everything, because you really have to add more ventilation in the attic. And that's about all I know as far as that insulation goes. What time for one more question? We got to go.
Well, I mean, what about putting a power ventilator in the attic where you can put on humidistat?
That can certainly work. A lot of people want to do it passively, and if you talk to roofers and everything, they have good concepts of what to do with passive ventilation. I would go that route first before I started getting into any power venting. Okay, I'm going to wrap it up now. Thanks very much for coming. I really appreciate your time, and we're going to be moving on to plumbing in a few minutes. Thanks again.